Oh, everyone, let's give a warm welcome to Dr. Stephen Wolfram.
Thanks very much. Well, it's kind of coincidental that I'm here right now because this is a downtime in the US between sort of Christmas and New Year and so on. And I'm a very hands-on kind of manager of our company. And I'm always keen to work with people. And this is a time when I can't work with most of my employees. So I have to take a vacation. And so I decided to take a vacation in China. It's been a very interesting, it's the first time I visited China. And it's been very interesting, and I've learnt lots of things, and I've met lots of interesting people and companies and so on. But I'm pleased to be able to drop in here today. It's an interesting time in the history of our company because we've spent basically about 28 years developing a large technology stack, and the results of that development are about to really blossom into a whole collection of new products and so on. And I can try and show you some of these products depend on the cloud and the internet and so on. And so there'll be a little bit of scratchiness in showing that to you here. But I'll try and show you some of the things that we've been working on and some things that I think are pretty important in people's ability to develop products using algorithmic methods and so on. So maybe just by way of introduction, I can try to show you, let me just show you very quickly, we've had two kind of traditional types of products. One is based on Mathematica, and one is based on Wolfram Alpha. So Mathematica is our kind of long-running system that we released 26 years ago now, which is a system for doing technical computation that's become very widely used in research and development organizations. In the US, for example, it's used, there are slight licenses for it at 90% of all the universities and so on. It's a very widely used system for doing research, development, education. About 5 years ago, we launched Wolfram Alpha, which is a kind of more consumer-oriented product. Its idea is to have as much knowledge about the world as possible and to be able to compute answers to questions that people enter in natural language. And so Wolfram Alpha has become a very popular website in the US particularly. It's also the engine that powers things like Apple's Siri intelligent assistant and provides the knowledge results for that, and powers a bunch of other intelligent assistant applications from other companies and so on. The feature of Wolfram Alpha it's a very ambitious project. The goal is to sort of capture as much of the knowledge, as much knowledge about the world as possible, as much of what has been done in making knowledge systematic as possible, and to be able to automate answering questions on the basis of that knowledge. So let me not try and show you a live demo of Wolfram Alpha because I think it's going to get all messed up with internet connectivity. But I can show you a few queries live, and I'll show you some things that I just cached, just so that we can go through them quickly and not get stuck on internet connectivity problems. But the basic scheme of Wolfram Alpha is you type in a question and it types back an answer. So can people read this at the back, or should I try and make it bigger? Bigger? Is it okay?
They say louder, not bigger.
Louder. Okay. I'll try and see if I can eat the microphone here. Okay. Let me try. I'll make it bigger, and I'll try and be louder. Okay. So here's a really basic kind of thing that we might ask Wolfram Alpha. What's 2 plus 2? Okay, it'll tell us the answer is 4. It'll kind of give us a report about that answer. It'll show us a few other things about that computation. Let's try something else. Okay, here's more of a fancier math computation. We're asking it to compute an integral. And for better or worse, at this point, at least in the US, the vast majority of students who have math homework to do in high school and college are using this. So it's interesting to watch the waves of homework go around the world every day. But so what we try to do here is to answer the question and then kind of give a report about sort of other things that are relevant to this question. One feature that's very popular among the student crowd is the step-by-step solution mechanism that kind of shows you a simulation of what a human might do if they were solving this problem. So asking for the International Space Station, it's going to figure out the current position of the International Space Station. And so it's fairly typical. There's a feed of data that gives us some of the orbital information about the International Space Station, but then we have to do a computation to figure out where the space station is now and where the space station is visible from and so on. Okay, another more everyday kind of thing, what Starbucks are there within 10 miles of the town that I happen to live in? Other kinds of data, or something where we're computing a sort of synthesized nutrition label where we can say, we give some kind of natural language specification of some food, like who is speaking when during the play and so on. Or here's something where we're entering something that is interpreted as a genome sequence, and we're trying to and then what will happen is that we'll get this will look up where and there's huge amounts of code, huge amounts of data that we've accumulated. One might think. So then another piece of all of this is to understand the natural language. So what we're trying to do is to actually understand queries that are given by people sort of in free form. So we've done this in English, and at this point, in domains that are well developed for us, we're probably running at 97-98% success rate for people typing in a query and having us be able to understand that query and process it. In general, on the web, it's probably around 95% success rate, which we're pretty pleased with because it's been a long-standing problem to do that level of natural language understanding. The main critical advantage that we have over other people who've tried to do natural language understanding is that we have a very large knowledge base that is on the sort of back end of our natural language understanding. So, for example, disambiguating a term is quite easy for us because we actually have knowledge about what the term means. If somebody says Springfield, we know a lot of stuff about all the different Springfield towns that exist in the US, and so we're able to disambiguate things. So anyway, this is this is sort of the story of Wolfram Alpha. It's something where natural language comes in, we're using underlying knowledge and data, we're basically generating a report as output. There are sort of some variants of this that for example, we have a pro version that allows you to upload some of your own data and images and things like that and process them using our technology stack. In general, the Wolfram Alpha API gets used in things like Siri. It's also been used in a whole bunch of different kinds of startups and devices and so on to provide computational knowledge. Also, Wolfram Alpha in general, we have a whole business associated with using Wolfram Alpha on corporate data and building custom versions of Wolfram Alpha so companies can do this kind of natural language querying of their internal data, kind of combining it with public data that we have. Well, one thing that we're doing right now that might be of interest here is we've been spending, for the last couple of years, we've been trying to create a version of Wolfram Alpha that runs in Chinese. And it wasn't obvious that our natural language understanding system would generalize from English to Chinese. The basic way it works is we're translating the original natural language into a kind of precise symbolic representation that we can then do computations from. So we're using the same symbolic representation, but now we have kind of a front-end processing that's from Chinese rather than from English. I'm unable to test or type this because I don't know any Chinese, but I can just show you a few examples. These are some more scientific kinds of examples of Wolfram Alpha running in Chinese, it won't be as good as the English version when it first comes out, because the English version we had to watch 1 billion queries or something go through in order to learn what humans actually type to a system like this, and we'll have to do the same kind of thing in Chinese. But we're hoping that this will be out and that the API associated with this will be available in a limited number of months. So, okay, that's the story of our Wolfram Alpha system. I think the thing that's kind of the newest exciting thing for us is our Wolfram language. And the Wolfram language is what Wolfram Alpha is written in. Wolfram Alpha is probably 15 million lines or so of Wolfram language code at this point. But the Wolfram language is what is sort of the what underlies all the technology we're doing, and what I think is probably most what's that trying to do? No, the sort of our big big thing for the future. Just one second here. Okay, so let me try. Okay, so the idea of the Wolfram language is to have a language in which as much as possible is automated. So traditionally in computer languages you have a language where the actual language is quite small. Maybe people have written libraries and things for it, but where there's not much knowledge built right into the language. Our concept in the Wolfram language is to build as much knowledge as possible right into the language, with the objective to make it as easy as possible for programmers to do what they want to do. So let me try to show you a little bit of what we've done. Now the question is whether I'm going to be able to... Okay. Doing this one-handed is going to be slightly challenging. Let's see what we can do. If there was a piece of string, I could just tie the piece of string around the microphone. Okay. There. Or I can do this. I think it's going to be tough one-handed.
Yeah, just going to make a minute.
Okay. Well, here we can start off. So the basic form of interaction with the Wolfram language, there's one of the important features is that it can be used as a completely interactive language. So we have these documents we call notebooks that we actually introduced for Mathematica 26 years ago now, that are a way of having essentially a session history together with you can have this. You can type in. You can make a complete document here that contains active elements. So, for example, we could just do a computation here. Okay, there's the result. Big long number. Look at this. This is great. I wonder if it's directional.
I really can hold it. It's really good.
Let's see. I feel like one of these singers who's doing Okay, let's see. If we can, okay, you know what would solve this? If we could move the computer up. Okay, I think this is going to work. So let's start off doing some things with the language. So we can start to set up all kinds of things. Like there's a sphere, we can rotate it around. We could. The idea of the language is to be able to handle all kinds of data. So we can, if we want to make some graphics, we could say, plot a sine curve. We could say, we could make this interactive by saying manipulate the plot of the sine curve with that varying from 1 to 5 or 1 to 15, whatever. Now we'll have an interactive control thing here. We could as well do that with some data. Let's say we make a table. Let's make some fake data. Let's make a table of the first 1,000 prime numbers. Okay, there we have it. Now we can just say, make a plot of those. Maybe we can say plot differences between those prime numbers. So we can start to generate all these plots of data and so on. And we could, it's easy to create all sorts of visualizations. Well, we can deal with all sorts of things. Like let's say we make, I could, for example, connect to a social network and use the API of the social network to extract my friend graph, or I could do a pretty good simulation of my own personal, for example, Facebook graph by just making a random graph here. That's a random graph with 100 nodes and 200 edges. Now I can take that graph and I can go ahead and say, make a community graph plot of that graph. So now it's doing an analysis of what the sort of separated communities within my friend network are. Well, we can do all kinds of things with graphs and networks. We can work with all sorts of different kinds of data. So for instance, let's get an image here. See if I can make this work. Let's do it again. Okay, there we go. So there's an image of me eating the microphone. Let's see what we can do with image processing this image. So we can, for example, we could say, let's do edge detection on that image. There's the result. Let's say we want to do a dynamic edge detection. So we can say dynamically edge detect the current image from the camera. And then so, the idea in all cases is to be able to have a language where sort of everything can be done in a coherent and automated way. So, for example, let's say I partition that image into little blocks of size 20 or something. Now, let's see, what could I do with this? For example, one thing I could do, let's say, I could sort each row here, and then I could assemble these back into an image, or I could take there's a kind of weird image there, or I could, for example, do something like let's see, what could I do? I could take something like this, and I could say manipulate this with something where I'm rotating each thing by a certain angle, theta, and let's do that. Let's say at level 2 here, and then let's say theta 0 to 2 pi. So now what I should get, let's see, so now I've got that, I've got a little control here, and I can go and start spinning those around. And all these different pieces that are needed, whether it's image processing, or manipulating lists of data, or rendering the things with rotation and so on, all these different pieces fit together to make to let the system work. Well, okay, so we can deal with all kinds of data. Like for instance, let's say we look up. We have an English dictionary here. Okay, so there are 100,000 words in our English dictionary. we can say what's the length of each word in the dictionary. Now we can say make a histogram of those word lengths, and then we'll see the distribution of lengths of words in English, for example. Or we could, for instance, we could say take those words and let's just take the first letter in each word here, and let's do that. And then let's just count how many. Let's make a tally of how many of each of those letters occurs. Oops. I want to do. Let's do this again.
Tally is a mathematical function.
Yeah, it's just a Wolfram language function, which it's just tallying up the number of occurrences of something. So here, what we can do. Let's say I want to make. Everything I'm typing is just a built-in Wolfram language function. So let's try, see if I can do this. Not sure I can necessarily do this programming in real time, but I'll do my best. It's more fun to see the real-time version of the programming. Let's try. Oops. What I'm going to do is try to. Let's try that. Yeah, there we go. Okay, so what this is doing is it's making. It's showing the distribution of numbers of words that have different numbers of first letters, and I just created this output like that. I could say, I could make a row out of that. So then this would be kind of a little bit of an infographic of what are the popular first letters in words in English. Okay, so to me it's kind of significant that one can get stuff like this out with a smaller piece of code as we have here. Okay, well, so there's a lot of so the idea of the Wolfram language is build as much in as possible, and part of that is about building in algorithms, building in ways of doing computation. Another part of that is about building in data. Now, to really get this to work beautifully, I will have to connect to our knowledge server, which is in the US. I'm going to cheat a little bit, and I'm going to use some cache data that I have on this computer that may or may not work perfectly. If we have to connect back to the US, it will just be a bit slower. But let's try and start doing some things. So one thing we can do is, let's say we type in something like this. Let's see if this works. Good, that worked. Okay, so in our language, in addition to having information about, the words in English and so on, we also have information about entities in the real world. Like New York City is an entity in the real world, and we can ask questions about that entity. For example, we could say, what's the population of New York City? And it will give us the result. This is using the same knowledge base that we're using for Wolfram Alpha. We've got lots of different kinds of things in that knowledge base. Let's say, for example, we ask about planets. That's just so we can say what's the list of. Let's make a list of planets here. Okay, there's a list of planets. Now let's say we can say get us an image of each of those planets, and this is part of our built-in data. Is images of those planets. We could also say something like, let's take that and let's find the mass of every planet. Oops, that's not what I wanted to do. Let's get the mass of every planet. Okay, there's the result. And now, for example, let's say we want to make kind of an infographic where we show every planet at the size corresponding to its mass. Okay, so now there we'll get a result that shows where we've created that and shows Jupiter is very big relative to other planets. But again, I find it very, very. I like it very much that it's possible to create an output like this with as tiny a piece of code as we have. And the reason that's possible is because we have all this knowledge built into the system. Well, we can do all sorts of things. Let's say, here's an example that might work. Let's say we get some data on something a little bit more consumer-oriented. Let's say we get a list of. Okay, so we've got data on about 30,000 movies. So this is a kind of a random selection of movie titles here, and we could go ahead and say let's get the movie posters for these various movies. Okay, so there's the result for those movie posters. Okay, some of them aren't available. Let's go ahead and delete the ones that aren't available. And then we can go and say, for example, let's start doing some image analysis on these movie posters. So we can say, let's say, get the dominant colors in each of those movie posters, and now we'll go ahead and do an image analysis on each poster and show us the list of dominant colors. And we can go ahead, for example, and plot those colors in the chromaticity diagram. And so it'll show us, what are the popular colors that artists have used in those movie posters. So these are types of things that we can do. We can also. Let's see, did that stop working? Oh, maybe not. Oh, I see. Yes. It's okay. It's directional. So we have all sorts of information about the thing is very aware of. This is it. It thinks I'm in the US. It's confused about the where it is and so on. But we can go ahead and do something like this. We can say we can look at a place, let's say the Eiffel Tower, and we could, for example, say generate some geographic picture. Let's say we say make a disk around the Eiffel Tower with a radius of 10 miles. That works. Okay. And now show that as a piece of geographics. And if this works, it should retrieve. There we go. So there's a map of showing a disk around the Eiffel Tower, a 10-mile disk around the Eiffel Tower. If we want to be a little bit more ambitious, let's see if we can make a thing where. Let's be a bit more ambitious, and let's just make something where we have we make a sequence of pictures where we say. Let's try this. Make a disk. Let's see there. Yeah. Make a whole collection of these maps going from a radius of 1 mile to a radius of, let's say, 10,000 miles. This might take a little bit longer, but again, this shows us kind of the code that we're building up here. So that goes from there's the first image that shows a bunch of streets in Paris. And there's the final image, which shows basically the whole Earth, except for the part that isn't in the disk, the 10,000-mile disk around the Eiffel Tower. So these are, again, things that we can do based on the knowledge base that we have access to in the Wolfram language. I might mention some other kinds of things that are possible. We have a whole machine learning infrastructure that we built. See, one of the general things is that we've implemented huge numbers of algorithms and so on about all sorts of different kinds of things. And the thing that's been really, really exciting to us in recent years is because we've maintained this very coherent system that knows about strings and graphs and images and geometry and sounds and time and engineering data and so on, when we want to add some new kind of functionality to our own system, it's vastly easier because we can build on these very coherent building blocks that we've already assembled. And so, for example, in recent times, we've added a lot of state-of-the-art machine learning capability to the system, and we've been able to implement very, very nicely sort of all the latest and greatest methods in machine learning. What's been particularly useful is that we've been able to automate, we've been able to build sort of a meta-algorithm, and this is a typical thing that we do. We have a lot of individual algorithms for doing things, and then we create a meta-algorithm that, for your particular data, will pick which of those underlying algorithms should be used. So, for example, let's do a very simple example of machine learning. Let's see if this works. We could try importing something, let's say the front page of the United Nations website. Let's see if we can import that. Okay, there we go. That was a small piece of data. Now we can just say, split that at every new line. And now we can say, let's classify those lines according to the language that particular text is written in. And so there we'll be using a built-in classifier there to just decide what language each of those is written in. Now we can go ahead and try and, it might take us a little bit more effort. Let me see if I can do this. I might have an example here. Okay, so here I might have I think I can get you up an example that might be a useful one to see. So let me pull up some code here. So I'm working out for Picasso. We have data about all sorts of things, including like painters. And the machine learning task I was going to try to do was, can we recognize whether a painting was painted by Picasso or Van Gogh? Okay, so here's a bunch of Picasso paintings. Here's a bunch of Van Gogh paintings. Here's a collection of images. Let's say 20 Picasso paintings, and let's say 20 Van Gogh paintings. And now, let's see, I can probably get some code here that will make me essentially, will set this up as kind of a training set for my machine learning system, where it says that's a Van Gogh, and down here somewhere it will say that's a Picasso, and so on. And now what I have to do is just to say classify, create a classifier that classifies paintings according to whether they're Van Gogh or not. Let's see, so now I need to find, well, let's see, I need to get another sample of one of these paintings. Let me go ahead and get one here. How about I pick, let's say, if this works, let's get, let's say, paintings 30 to 35 of that list. Okay, well, there are at least a couple of paintings. They're very weird looking for this. I'm going to try and choose some other ones here. Oh, whoops. Okay, let's try this guy here. Let's say we use our classifier. That was the output on line 31. Let's use the classifier and apply it to this painting here. And it concludes rather incorrectly that that's a Van Gogh painting. So I guess this is what we get for training our machine learning classifier on only 20 paintings. But if we had a few more, it would have a better chance to get them right. Let's see whether it gets this one right. This is life in the world of. Let's try that one. Maybe we actually set up the data set the wrong way around. I'm not sure, but anyway, you get the basic idea. And with large data sets, and we can deal with very large data sets, this will be, the idea is automate out the need to have a machine learning specialist, so to speak, figuring out what method you should use. In this particular case, it used random forests to do this particular piece of machine learning. Okay, well anyway, so this is kind of the concept of the Wolfram language when it is just running locally on a computer. Another big thing that we want to do is to make the Wolfram language interact with the cloud. And in fact, everything that I was doing here today, I could equally well have been running in the cloud just in a web browser. So this whole notebook interface is actually available directly through a web browser. It's not quite as smooth as it is on a computer, but it's getting close. I think I will not tempt fate and show that here right now, because it will be kind of slow to run it against our cloud in the US. When there's a version of this cloud in China, it will be hopefully nice and fast here. But let me show you, let's see if I can get this to work. I want to show you, wait, bad sign. Okay. I'm trying things that I've created here in our cloud. So let's go back and let's pick some input that I had here. I don't know, I could maybe pick, how about this guy? Let's pick this particular piece of input here, and let's go ahead and say down here that I want to deploy that to our cloud. Okay, so I can just say cloud deploy, and I got that big piece of input here, and now I hope that everything works, and it will be sending this to our cloud. Come on, it should be faster than this. This is usually instantaneous, so come on. It's yeah, let's hope this wasn't completely blocked. That would be a shame, because this is really cool to see. Well, I'll tell you what. Let me see if the problem is that we're trying to send. Let me see whether I'm trying to send too much data over. Let's just do something a little bit smaller here. Let's just try to send that over. Okay, we got something back. All right. So what this did was it created a website, and that website, if we can get to it here. Let's say, I seem to often use an example to do with cat breeds. It's in the theory that cats are popular on the internet or something. Let's say we want to do something where we're creating a form where we're going to type in the name of a breed of cat, and we're going to just generate a picture of that cat breed on the web. So this is defining a form with one field, breed, and this is now I'm going to say deploy this form to the cloud. Oh, come on. Well, okay, who knows? Maybe this worked. Nope, that didn't. Okay. I'm going to try it one more time. I know what. This is, it's a little bit of an alien environment here. Let me just see. Try this. So this works. Come on, wake up. Good. Okay, that might have worked. Okay, so now this again deployed to our cloud, something that, it's using a kind of responsive design here because I made this very big. Let me make it a bit smaller. So now it's going to ask me to type in a breed of cat. This is a smart field in the sense that it's using our natural language understanding stack to let me type natural language. It's expecting a breed of cat here, and it will generate a picture. Now, if we wanted to, we could modify this. We could say, let's change our little app to make it also have an angle to fill in to specify, we can rotate the cat image by some angle. So let's go ahead and do that. Say, rotate this by an angle in degrees. So now we can deploy that again, and we should get a form with two fields. There we go. And let's try a different kind of cat and some angle 79 degrees. And so now we should get a rotated cat as output. So this is how you would basically deploy a web app from our language. And again, the computation is running in our cloud. The interface is running on the web. So let's say you want to include this in a piece of code that you're writing in another language. You can create an API in the cloud as well. Instead of a form in the cloud, you can create a RESTful API. So here what we're going to have to do is to say, okay, we're going to give a parameter breed equals Manx, for example, and then angle equals, some number, and now this will then run this as a RESTful API, and we'll get a different cat here. So what you can do is to take that API and embed it in another program. So you can, for example, say, this is not going to do an interesting thing. What I wanted to do was to take that API and what I just got was the embedding to put the thing into an iframe and so on. What's more interesting is to do something like, say, show me the embedding for Java code, for example, where I can just create the Java code that from within a Java program, I'm then calling out to our cloud to get the computation done and getting the result back into my Java program. So the idea of this is to make it easy for people to integrate our cloud and our technology into whatever applications they're building. So this is so there are lots of other pieces to this picture. So for example, one thing you might ask is, what about deploying not in our cloud but on other kinds of devices? And for example, a year ago now, we started bundling the Wolfram language with all Raspberry Pi computers that are out there, and you can expect that there'll be other solutions for having the Wolfram language running as an embedded language inside small devices and so on. We've had a whole big effort in being able to connect to external devices. We have a whole framework for doing things with devices. Let's see, we can, for example, if you say, if I'd connected a device, if I connected something to my computer, I could, for example, read a time series of data from the connected device, and we have a lot of different drivers for different kinds of devices here. I should mention one thing, since one neat coming feature is that our language is basically makes use of the fact that its keywords are words in English, but if you happen to mainly know Chinese, you can go ahead and annotate the language with Chinese, so you can show a Chinese phrase for each of those keywords. And actually, you can also use our natural language understanding system to input things in, for example, Chinese, to be able to find the functions that you want to use. Well, anyway, back to devices. So the idea is that this language can exist embedded on devices, and that we can connect to lots of different kinds of devices. Something we have coming very soon is a thing we call our data drop, and that's a way of getting data from even the dumbest of devices into our system. And the notion is that we provide a whole bunch of interfaces to put blobs of data into our system. So there's an API, you can send email to the cloud, you can have a little piece of embedded code, you can put things in from a web form, you can put things in from a mobile app, you can do all kinds of things to just get blobs of data into our cloud. And the notion is that you can, and I doubt this is going to work, but let me just see. It's conceivable that this will work. Let's see. It's not going to work. Okay, never mind that. I was going to try and actually create a data bin, which will then just have an ID, and you can then push data into the data bin from anywhere, and then within our language, you can then access that data bin and analyze the time series that come out of the data bin and so on. And then every place that uses our language, even intelligent assistants like Siri, will be able to get access to the data that you've pushed into that data bin. So if you have some kind of connectable device, you can just connect that device to our data drop and push data into our data drop, then analyze the data within our language and have it come out in lots of different places. In general, there are lots of ways to have things to create output from the system. So this is I mentioned that these documents, the thing I'm typing into is one of these things we call notebooks, and we can have we can type text in here, and we can say, let's put an expression in here that says heading created now, and let's say we say something like let's put something in here where we're saying I don't know, output is, and then we can put let's put some number to compute here. So this is now a template that allows us to create essentially an automated report. We can just say generate that, and it'll tell us the heading was created at this time, and the output is this thing that was output there. From within our cloud, you can then use this to kind of do data science and so on, where you're getting input from different databases or feeds or whatever else, and then automatically generating reports in the cloud that you can get sent to you or get posted on a website or get automatically updated every minute or something like this. So this is a really convenient mechanism for that. Well, lots of different things. Oh gosh, there's a lot of different things we can do. One of the important features of this whole language is that it is a symbolic language. So, in most languages, if you just type X, the language will say, that's an error, I don't know what X is. In our language, X just stands for itself. And that's sort of critical in everything the language does, because that's what allows us to represent all these different kinds of things, whether they're graphics, or whether they're cities, or whether they're even programs that are running elsewhere can all be represented as symbolic expressions. So there's a whole framework, for example, for doing parallel computation that makes use of this sort of symbolic representation of code along with data. So, for example, here, this particular machine probably just has 4 CPUs. So if I go ahead and say, make a table of 15 copies of just computing process ID, I'll get that. Just started up 4 kernels on this machine, and now I'll just get these. It will distribute that very trivial program across the CPUs on this computer. If we were in the cloud and we had things all set up correctly, we could distribute this across 1,000 different instances of our engine and so on. And in fact, for example, in Wolfram Alpha, the way that it works is when a query comes in, it's distributing computation across a whole bunch of different instances of the engine. Well, anyway, so that's a little bit of introduction to what the Wolfram language is about. I think among the things that we're excited about right now, a couple of things. One is that if people want to learn to program, this language is a really good one for them to learn in, because it's a language where you can immediately do a lot with a very small amount of code, and you can immediately connect what you're doing to very real-world kinds of things. You can actually write code that is making use of knowledge and information about the world at large. Actually, one little cute demonstration that we made of sort of how short the code can be in our language is we have a thing called tweeter program, where we're saying write a program that's less than 140 characters long and see what it can do. And it's kind of remarkable what kinds of things you can get done in 140 characters in our language. So, you know, all kinds of different things that take only 140 characters to specify, and they will and you can do them in the language. So it's very it's a very succinct language where sort of the humans have to do as little as possible to get interesting things to happen. We think one of the interesting applications for that is it's a language that people can easily learn, and it sort of breaks down the barrier between sort of the programmer and non-programmer. Another important thing is that it's a great language for powering things like startups, because kind of the notion is if you have an algorithmic idea, this is trying to provide the fastest path from that idea to an actual production-grade implementation. And the way we have our cloud set up for the kind of playing around and trying to implement things, it's free to do that in our cloud. We hope to make a good living from lots of very successful startups that deploy serious products in our cloud and are running billions of queries per day against the cloud and so on. But the idea is that this is an environment where one can go from kind of an algorithmic idea to an actual working production piece of code in an extremely short time. I should mention that in addition to being able to do this on the web, you can also do this on mobile. On iOS, you can either use a fancier SDK, or you can use our Cloud Viewer app to let people get to the various apps that you've created. On Android, you'll actually be able to create a separate APK file that's a complete app that will run against our cloud. I might mention that for sort of the fancier applications, our cloud, we have a public version of our cloud. We're also having private clouds. We also have an embedded version of our engine. So if you have an application where you want to run the whole system locally, you can get an embedded version of our engine. And all you have to do is when I did that embed code thing to connect to an API in the cloud, you can target that instead to connect to a local library that's an embedded version of our engine. So anyway, this is what we've been up to. This is a kind of a funny moment for me, because these various things that I'm talking about are mostly in beta, just sort of getting ready for their grand release. Yes.
A question. How does this relate to the semantic web? Does it use the semantic web? Does it enhance the semantic web?
Okay, so That's great. I was about to go to let's do questions, but we have the first good question, which is about how does this relate to the semantic web? So our approach in building Wolfram Alpha, we've effectively had to create a very broad ontology for the world. The ontology that we've created is not like the traditional semantic web ontology that uses RDF and triples and all this kind of thing. It's a more algorithmic ontology, because what we've realized is that's actually the way the world is. Having a static ontology that represents, planets in the solar system, it's not all that useful. The planets in the solar system move according to algorithms, and you need those algorithms to kind of represent that aspect of the real world. But what we have is we have something that we have kind of a canonical way of representing things in the world that we've built for Wolfram Alpha, and so that means when we talk about New York City, for example, there's a canonical symbolic identifier for New York City. The same is true for any chemical you can, for millions of chemicals, or for all sorts of other kinds of things. In general, we have a thing we call WDF, Wolfram Data Framework, which is a canonical symbolic representation for real-world kinds of things. Now, what's really interesting, I think, is that with our natural language understanding capability, we can go from your kind of unstructured linguistic description of a thing into that precise WDF canonical symbolic description. And the way that works is in the language, we have this notion of a thing we call an interpreter. And so an interpreter would, for example, say, I'm going to be looking for a city, and let's say I just say New York, NY or something. And then what will happen here, assuming that everything is connected and we can get to our server and all that kind of good stuff. There we go. Okay, so what this did was it took that natural language of New York, NY, and it turned it into this canonical identifier here. So similarly, if I say, I am worried that there's something very weird is happening here, because this is echoing my keystrokes only very slowly. So let me just, I'm just going to save this file. I'm going to restart because I'm worried that otherwise something terrible is going to happen. Let me just, I'm just going to restart this. Okay. Let's now we should have a nice fresh so here, okay, so what I was showing was how we can go from kind of a linguistic description. So for example, if I say interpreter and I say something like it's got to be a number, okay? And then I type in, or in fact, it's got to be what we call a semantic number. I could type in something like, let's say 2/3 here. And then what should happen, there we go, we get the 2/3 there. Or for example, if we say something like interpreter, and then I say something like a computed date. And let's say that my date is 3 days after Christmas. So what should happen there is then we can, so if you think about using this in an environment where you're putting up a web application or something like that, you can have a field there which just says enter a date. And the person can either type an explicit date or they can type something like 3 days after Christmas. And in both cases, as far as your code is concerned, it's represented in this canonical symbolic way. So that's kind of what we're doing, is to try to do something a little bit like the semantic web, in the sense that we've actually got an ontology that we have debugged really well through Wolfram Alpha and through what we've done with the Wolfram language, and we're then providing ways to go from unstructured natural language and natural data into that ontology. So that's the basic strategy that we have with things like the semantic web. Okay, well, that was our first question, but I hope there are others. Yes, please.
Yeah, I have a related question, but it's not about the semantic web, but what is missing to get natural language processing? there, right there, without the function, without writing 1, dot, 10, it's just tell the computer from 1 to 10.
But, I'm sorry, you're asking how is that done, or you're asking...
Hello. The question was, right now you have a wonderful interpreter that can get an abstraction layer, and we have a symbolic interpretation of data.
Yes.
But what is missing? How do you see in the future
Getting rid of
syntax? How do we leverage this resource of natural language processing?
Purple frame, correction. Not for free pieces of code in the Wolfram language, either in an open source fashion, with the source code, open code fashion, where the code is readable, or with the code not readable. We've actually had a project for a long time that is now a large repository of Wolfram language code. This has been something that... Okay. Well, this is not our thing. If I could get to it, there's a thing called demonstrations.wolfram.com, which has about 10,000 open code examples. They were primarily created for educational purposes, but they're a really good resource for seeing Wolfram language code and being able to build on it. Maybe it is a typo. Yes. You are right. There was a typo there. So let's try it one more time. Well, there was a pop-up that tried to open, which seems suspicious. Let's see whether that happens. In any case, so what we've tried to do, we've tried to make our system as connectable to the rest of the world as possible. And so you can call Java code, you can call C code, you can call our system from within those systems, and so on. We're also trying to make our mechanism for doing hookups to devices as modular as possible, so that people can contribute device drivers and so on. So that's our plan. But we're this is something that will develop over the coming months and years as all of our cloud infrastructure rolls out.
Yeah, and as a developer, we use GitHub, so which is more comfortable for the open source community.
Yes.
So would there be any possibility to?
Sure, it's absolutely, and we're trying to. So we have a thing called Wolfram Workbench, which is an Eclipse-based IDE for the Wolfram language, and that. Anyway, that's an Eclipse-based IDE for the Wolfram language, and you can connect that to Git. Git is the system we use internally for our own source control. So we have pretty good tools for working with it. In fact, you can also, not yet out, I guess we've developed for our own internal purposes a connector between the Wolfram language and Git, so that you can actually do analyses of your code within the Wolfram language. And we've also, in the Wolfram Workbench, actually, we have some fairly sophisticated code refactoring capabilities, which use the fact that in our language, everything is symbolic, so code is just another form of data, and you can make transformations on code and so on. But definitely, and we're also working with some cloud IDE providers to make our cloud and our language accessible within these various cloud IDE environments. I mean, our goal is to make the language as accessible as possible, and we're always interested in more ideas about how to do that. But Git and GitHub and so on are very much on the roadmap. Yes? Whoever can get the microphones.
Hi. So I'm Lausha, and a designer. I work for and I'm helping form a group called Lifesaver Labs. And I've become very interested in STEAMing too. So STEAM, the acronym, Science, Technology, Engineering, Arts, and Math. But if you put an exponent on it, it could become moral mathletics, right? Moral math marathons that we can help drive through maybe some slight modifications or computation over some of the deepest and most serious tragedies that we've suffered in different nations and regions through the world. So just recently here in Shanghai, we lost XinCheJian lives. 36 people died in stampede. People were crushed near the Bund. And it's not possible to know how many years of life were lost in that event. If it trended to the young, it might lead to a different result than if it trended to the old.
Is there a question?
Yeah. So this is the September 11th data set for the number of people who died and their ages. And I'm wondering is if you could help journalists compile lists of individuals who died or were seriously injured and create an easy-to-reference system of equivalence for those tragedies so that we can compare one tragedy to another and understand things in their totality, like the Sichuan earthquake as compared to September 11th or the tsunami disaster.
We are mostly tool makers in the sense that we're just building tools for people to we're not really in the business of coming up with conclusions. We're more in the business of building tools. I will say, a few things I might comment on. It's kind of grim, but we certainly have in Wolfram Alpha we have all sorts of mortality curves and so on, and we know all sorts of things about life expectancies and so on. That's not the in the particular thing you're asking about, given an age, how many what's the likely number of years of life lost and so on. Not the kind of thing one likes to compute about, but we certainly have the data available to be able to figure something like that out. In fact, quite a number of newsrooms use our technology to make computational news, so to speak. So it's pretty common for people to some of the more sophisticated newsrooms, particularly in the US, have made lots of use of our technology to be able to make the impactful infographic as quickly as possible. I think there was that's something that I think we can be very useful on. We ourselves, because we have a team of people who like doing R&D kinds of things and like using our tools, we quite often, when there's some news event, we'll actually do some computation around it. It tends to be, we tend actually not to usually release the results of that because usually too many news events have bad things happening, and we don't really want to be, we don't really want to connect ourselves necessarily to that. But certainly in things like, I might say that when it comes to computations about the world, so to speak, I think we're in a sort of interesting position because we have a lot of data about the world, so we're able to actually do computations. We're also able to simulate lots of kinds of things. I must say that I know some science that I've done in the past to do with these things called cellular automata. That happens to be that happens to have turned into the standard methodology for doing road traffic flow computations. Actually, it's kind of ironic because I myself was interested in road traffic flow a really long time ago, before I started working on cellular automata, and then I worked on cellular automata. I never went back to road traffic flow, and now it turns out the standard models use my cellular automata and stuff. But I know there are also models actually for crowds and so on that use the same kind of underlying scientific ideas. So that's people tend to use our language to make those kinds of models. So some things that can happen there. We're also we're trying to when it comes to data sets of news interest, so to speak, we have a program that will be starting up soon for having a data repository for storing interesting research and news kinds of data sets. That's again a different kind of story. But not sure that really responded to what you were asking, but those are a few comments. Yes, please. Well, wherever you can get a microphone. I'm sorry.
Thanks. So you have a marketplace for programs? Do you have a marketplace for data sets where people could monetize their data sets?
We're trying to do lots of things. We've got so we are going to have a data repository, and that's that will be monetizable. The sort of primary use case for our data repository is for things like researchers who have underlying data, and our concept is to let people do what we call data-backed publication. So, you've written a paper, it's some medical, clinical trial or something like this, and there is underlying data behind what you've done, but there isn't a good place to put that underlying data. And so we're trying to provide a standardized data repository that uses our WDF system for representing the data in a canonical form. Kind of the goal is that in the future, when somebody publishes a paper, for example, you'll see a graph in the paper, and it will have a link that links back to the code that generated that graph and the data that was used for that graph, so that you can mash that up with something else or use it for other purposes. But that's our primary case. We're also interested in the monetization of data sets, although I have to say that we haven't been encouraged by some other people have tried to have monetizable data repositories. So far that hasn't been terribly successful. I think we have a different situation because we can really immediately let people do things with the data, and so that we're definitely interested in that, but it'll be a little while before that happens.
Just a follow-up question. So my corporate data, can I push it and build everything in there safely, basically?
I'm sorry,
our own data set inside the company, right?
Okay, so for that you would use, there are really two options for that. You can use our public cloud, and you would have your own area within our public cloud, or you can have a private cloud where you are either virtually, it's either virtually hosted or hosted on premises, and we just started selling private clouds about 2.5 weeks ago, and it was very encouraging that a whole bunch of large companies kind of very interested, even though we haven't really started marketing these things. So I think that's a good option, is to get our whole, it's basically a clone of our whole cloud infrastructure in a virtualized or on-premises way. And I think that's probably if you really, really care about your data, that's probably the place to put it. We think our public cloud will be secure, but it's better if it's on your premises.
I have a question. I'm really excited by all that you've shown. It's really amazing. I'm wondering how you were able to take so many different domains of data and be able to kind of create this coherent, canonical, symbolic way of representing all of that across the company. And can you imagine large parts of the world, students and other researchers being able to contribute to that and still be able to maintain that coherence and to be able to be used across domains?
Right, well, so, when we first started working on the Wolfram Alpha project, it seemed like it might actually be impossible, because there's just too much data, too many different domains, and so on. And, I had the interesting experience, we were doing a field trip. We went to a big reference library, big room, lots and lots of books about lots and lots of different subjects. This was probably 10 years ago or so, when we were, more than that now, early in the project. And it looked very daunting, because there are all these different, there's a huge room full of books about lots of different things. But, we went through and we're like saying, well, this is a section about, financial data, this is a section about this kind of data. And gradually over the years, we've been able to go and cover a large fraction of these domains. It turns out that the number of different kinds of data in the world seems to be, it's large, but it's not infinite. It's something which is manageable. Now, we've covered a couple of thousand domains by now in a deep way. I always think, okay, we've done 1,000 domains, for example. The 1,001st domain is going to be somehow easy, right? That's never the case. There's always some new little twist that comes up in some new kind of data. One of the things that's been important in what we've done is sort of a meta level of thinking about this project, is one could start by saying, let me invent a theory of the world and then try and make everything fit into that theory of the world. Okay? Well, I happen to have spent some part of my life doing basic science and trying to do things about sort of making very global theories of things. But in this project, I decided I would take a more kind of humble point of view and just say, I'm not going to try and make a global theory. We're going to build every domain separately, and we're going to see what commonality develops between those domains. And that's been very successful. And so as we built out different domains, we're able to see common themes, and then we're able to build sort of higher level domains and so on. And that's been the way that we've been developing things. Now, in general, the problem of maintaining sort of a coherent design across the system, this is the story of the last 30 years of my life, is basically trying to do that. And, I think what's happened is, I have a definite design methodology that I've taught to a fair number of people now, and but when it comes to the actual design of our language, it's been me basically going through and approving all the elements of the design and kind of polishing the thing. And I think that's, it's a lot of fun for me, so I'm not complaining. Because, among other things, one has to really learn each of these domains at some level of depth in order to make a correct design. And that's something that personally for me has been very interesting. But it's something where, I think that the fact that I've been sort of able to provide leadership in this area has been sort of important in maintaining this coherence. Now, I have to say that within our company, for instance, we've now got pretty good methodologies for understanding whether a design is good or not. There are many precedents for any design. There's a pretty good methodology for knowing whether it's going to be successful. I end up doing sort of the final finishing touches, so to speak. But in many areas, I'm happy to say there's not a lot of finishing touches to be added. People within our company, for example, have been able to learn these design methodologies. But that's, I think it's a somewhat scalable thing, but I think it still requires leadership to keep things coherent. And, that's the story of my life, basically, to provide that. Hello. Yes, please. And then
So far you've captured over 2,000 domains of knowledge, and I'm just curious, which domains of knowledge have been difficult to capture? What are some of the most kind of thorny ones, or it may not be prioritized as much?
Well, I'll tell you one that we just are adding now, which turned out to be much thornier than I ever expected, is cars. Cars have just a ridiculous set of different features and models and gears and this and that and the other. You would think it was straightforward, okay? But it's a mess. That's an example. Another one that was somewhat painful was sports, because sports have things where you think you have a single kind of entity, but actually there are games where one team plays another team and so on, and so it's a whole different set of binary and beyond binary relations between things. Those are a couple of examples where things have been a little bit messier than you might expect. Now, in every domain, there's a whole story about its data and where the data comes from and what the data means. Is the data accurate? Take a domain like weather, for example. So there are about 30,000 weather stations in the world. They are of different levels of reliability. There's all kinds of issues about when you have a weather result and it says, the wind speed is 0, right? Is it in fact 0, or did a bird sit on the little wind spinny thing, and that's why it said the wind speed was 0? You have to try and do some checking of nearby weather stations and so on. You have to figure out, you find two weather stations have wildly different temperatures. Well, it turns out one of them is on a mountain 10,000 feet higher than the other weather station that's only 3 miles away. There's a lot of messiness in basically every domain. And one of the meta things that we've discovered is basically you have to involve experts in each domain if you're actually going to get the right answer. And we've been lucky enough that within our company we have a pretty eclectic group of people who have a lot of expertise on a lot of different things. We've also been lucky that through our work in Mathematica and so on, a lot of the world's sort of leading R&D folk in lots of areas use our products. And so it's something which is kind of a lot of fun for our team and very valuable for us is, given a particular domain, it's like, let's figure out who the world expert is in this particular domain, and let's talk to them and ask them about, the validity of different data sources, the ways that one's able to do computations and so on. And we've kind of got a process for kind of extracting, learning that knowledge. Another thing that's been interesting is when we do computations from underlying data, there's typically kind of a textbook way to do the computations, and there's a kind of research level way to do the computations. What we've been fortunate in being able to do is basically pretty much without exception, get to the research level of being able to do the computations. Because the difference between the textbook way and the research way is typically, well, you have to be able to solve a nonlinear differential equation or something if you want to do the research thing. But we already have the capabilities to do that. And now it's really just a question of getting the expert knowledge about what the sort of appropriate research level way of doing the computation is. And that's been, our goal in these different domains is once we have a domain to be able to cover it sort of to the best level that anybody can compute anything right now. I'll give you another domain that has problems, is medical data about diseases and so on. So given symptoms, what are the probabilities of having different diseases, but it's a fairly small data set. But as part of doing custom Wolfram Alpha projects, we've actually done several very large Wolfram Alpha projects with some national and other healthcare providers. And so we've seen huge data sets of medical data that allow one to do very interesting automated diagnosis kinds of things. But those data sets are all private, and so we can't deliver them to the world. And that's an example of another kind of type of data frustration. Is the data exists, but for one reason or another, it's not deliverable at this point to the world.
Hi, Mr. Wolfram. I have two questions. One is, to what end would you most like to see your language deployed? That's the first question. The second question is, who would you most like to benefit from your language?
Well, I mean, my goal in part is, I've been interested in computation as kind of a way of understanding the world and a way of doing things in the world. And my goal for the language is to have it sort of become a ubiquitous way to get computation done for anybody, anywhere. I think that's so. The goal is to have it be as widely used, as widely deployed by people inside devices, all sorts of things as possible. In terms of who would I like to benefit from it the most, I suppose to me I find it really neat when, for example, with Wolfram Alpha, where we have a resource that we've made available to people. I just personally get a lot of satisfaction out of realizing that we've been able to take very sophisticated algorithmic capabilities and just make them available to random people, random kids in various corners of the world and so on. And for me, I personally, you're asking me what I personally want. I personally like the idea that sort of anybody can get access to a sort of level of expert knowledge and computation, and that's sort of a completely uniform thing, kind of thing that in part has been achieved at another level by the existence of the web and so on. I would like to be able to do that for computation and computational knowledge for a very broad range of people. I mean, right now, I'm kind of interested in the idea of kids being able to learn to do computation using our language, and I'm kind of, I have to say, somewhat perversely looking forward to the inversion that I think will happen of lots of kids knowing how to use this language pretty well, and lots of sort of older professionals not being quite as up to speed. And I think it will be, personally, I think it will be really neat when we have our marketplace up and running for it to be the case that people can, just define kind of micro jobs to be done with our language, and that some random kid somewhere who happened to learn the language can go ahead and do that and get paid for it and so on. I think that's neat. But that's since you're asking my personal point of view, that's my personal point of view on that.
Okay, here.
Yes. Hi. I'd first like to draw a cool analogy with Matrix. You seem like Neo because you're kind of bringing to field the software that was there the whole time. You're allowing the accessibility of the computing, so it's pretty cool. I don't know if you've heard that analogy, but you're letting us communicate with the machines, so that's cool. And I'm wondering what is the biggest change that you're conceivably seeing?
I'll repeat the question. I'll repeat the question. I think it's the easiest thing to do. Yeah, go ahead.
The biggest change you're seeing conceivably about making computing and coding ubiquitous and simplifying it so that it's accessible.
Right. So the question was about what's sort of the biggest world change that will happen from computation becoming widely accessible. I think one thing is there's lots of aspects of the world. More and more of the world will become predictable in certain ways. So, for example, we can often compute what will happen. You know, we throw a ball, for example. We might be able to kind of estimate where the ball will land, but actually we could compute where the ball will land. If we have some vision system that's watching the thing, and it's watching the trajectory and measuring how fast it is, and it knows the wind speed, because it knows that from weather data and so on, we can predict where it's going to land. And so I think one of the sort of meta-level things that will happen is a higher degree of kind of being able to predict and optimize things that happen in the world. I might say that at a general level, there's sort of the question of the role of the human versus the role of the machine. I think one of the things that I've been trying to do is to sort of automate as much of what the machine has to do as possible. So the kind of the ultimate picture is the humans define the goals, the machines figure out how to achieve those goals. And so in our language, what we're trying to do is to have the language specify what it is you're trying to do, and then it's up to the implementation of the language to figure out how to get that done. So, for example, if you say to the language, solve some sophisticated kind of equation, for example, there may be 100 different algorithms for solving that general type of equation. But the goal of the language is to figure out which of those particular algorithms is best to use for your particular equation. So the goal is to sort of automate as much as possible of what has to be done. So we as humans just have to say, this is what we want to have happen, and then it's up to the machines to figure out how to make that happen. I have to say, you brought up the matrix and so on, and I have to say one of my kind of sort of peculiar scenarios of, are the machines going to take over type thing. Here's a sort of peculiar version of that. As more and more becomes... So first of all, I think we will outsource more and more of what we do to our systems, our machines. I myself have been a big enthusiast of personal analytics, quantified self kinds of things for many years, and so I've accumulated data for 25 years about myself, and so, like every keystroke I type and so on, I record, and all sorts of other kinds of things. Occasionally I look at this data, and sometimes I learn shocking things about myself from looking at all of that data. But what's increasingly clear is that sort of our memories and our experiences can get sort of outsourced to our systems, and as our systems get to know more and more about us, they get to be better and better at doing things like predicting and suggesting things to us. And I suppose my scenario for the machine takeover is it's kind of the analog of using a GPS system to do navigation. You specify, you typically, at least for me, I don't try and read maps anymore. I just follow whatever the GPS tells me to do. And I think kind of the scenario ends up being at a time when the machines know a lot about us and are able to make good suggestions about what we should do next, that some fraction of people will just follow the auto-suggest menu, so to speak. And so at every, so in other words, the machines are taking over in the sense that they're the ones that are suggesting what we should do, and we're ending up much of the time simply following what the suggestions are. So it's kind of my sort of weird version of a science fiction scenario, but I think it's a much more benign one than many of the ones in science fiction, and it's one where, again, the role of humans is to define sort of the goals that we're trying to achieve, and then it's up to our systems to automate how those goals should be achieved.
Hello? I think this is an amazing presentation with amazing results and how the technology can help us and understand this world more. And another interesting topic, I think you already bring this up, is like we start to compromise ourselves and try to collecting all the data from ourselves. You can see a lot of wealth of technology and the census happened in this few years. I was thinking, it's like compare with the massive data and the massive knowledge in the world. Also, we have a lot of data about ourselves. Did you think anything like this engine can do this for like individual peoples and helping the peoples do something better?
Yeah, I mean, I've let's see if I can find it here. Let's see. Gosh, how to find this? This works. Yeah, so I mean, I've done quite a bit of collecting of data for myself. That's a plot, for example, of that's a strange plot of every piece of email that I sent as a function of time of day for about 25 years. Actually, that only goes to 2012. So this would extend further. In this trip to China, there'll be some weird little piece that you'll see because it's a different time zone from the one that I'm used to living in. But this is mostly showing the fact that I was working really hard on this big basic science project that got finished in 2002, and then I got to have a much more regular sleep schedule. I've got, you can compute all kinds of things. That's like keystroke data. That's data from let's see, someplace here I probably have. This is kind of my own personal daily rhythm of incoming emails, outgoing emails, keystrokes, meetings, phone calls, steps I take, things like this. So this is there's a fair amount of detail from that. We actually have a thing where we let people. Let's see, where is this? Let people use Wolfram Alpha to do an analysis of their Facebook profiles, and from that project we've collected a lot of anonymized Facebook data. So we can do all kinds of analysis of kind of people on Facebook. Like, for instance, we can compute things like if you're a certain age, what's the distribution of ages that your friends have? So like if you're age 25, your friends tend to be very close to age 25. If you're age 50, you're also friends probably with your kids' friends, and they have a little bump at smaller ages. And you can see all kinds of things. This is the like the probability that people are married as a function of age, for instance, based on Facebook data. Or something down here, these are actual clusters of friends based on Facebook data. Or you can say things like, here are different topics, like people get more interested in careers and money when they get into their 20s and so on. Or people get, actually here's an interesting one, there's a big difference, it seems, between men and women in their interest in movies. Or people get more interested in politics, apparently, at least based on Facebook, as they get older. And so on. So these are kinds of things that one can get. This is based on doing natural language processing and topic modeling on Facebook wall posts. So these are some kinds of things that one can do for analyzing sort of personal kinds of things. But I think the general idea of using kind of the supply of data that we leave behind in the digital world and combining that with these other kinds of computations that we can do, there's a lot of interesting things to do from that. And I think we're just seeing the beginning of kind of the applications of personal analytics and being able to do computations with personal data. Okay, another few things, and then just briefly.
I wanted to ask, in your career, what has been the key or the keys to your productivity? And the second one is, do you have any, being here in China, do you have any requests or any help that you want to ask the Shanghai community while you're here in China?
Okay, so the question was about things that have sort of helped productivity in my life. The second question was about things I'd like to get help from people in China. Well, we're trying to figure out the best way to deploy our technology in China. We're looking at different potential partners in China. We'd also really like to see lots of people in China do lots of interesting things with our technology, and we'd like to know what things you guys would like to see us do to make that as easy as possible. I think that there's a lot of potential around, well, a lot of potential which I'd be interested to chat with people about. As far as my personal trajectory and career and so on, I've had kind of a slightly unusual personal trajectory. I started out, I grew up in England, and I started out pretty young being interested in science and so on. I particularly was interested in physics, and so I started doing what people had to do in those days, which was reading lots of books, because the web didn't exist yet. So I got to the point where I knew a fair amount about physics, and I started doing physics research, mainly because I was more interested in solving problems that people hadn't solved before, rather than doing kind of school exercises that people had solved before. So I started publishing papers about physics when I was about 15 or so, and then went on sort of playing physicist, so to speak. I got my PhD at Caltech when I was 20, but one of the things that happened was I discovered a very important personal secret weapon, which was computers. And in particular, when one does physics, one of the things that happens is one has to do a lot of elaborate mathematical calculations, which I was never very good at. And so I said, these are very boring, there's got to be a better way to do these. Well, why don't we just automate this? Why don't we make a computer do all this boring stuff? So that's how I ended up starting to work on doing mathematical computation by computer, and I built my first big system for doing that around 1980. At that time, I was a professor, and a young professor, I should say. One of the things that happened was that I realized I built this big piece of software. It seems pretty useful, not just to me, but to lots of other people. What should be done with it? Oh, I should start a company around this thing. So I started my first company. I made many mistakes in my first company. That was a very educational thing. And then I worked on basic science for quite a long time because I was interested in using a bunch of the tools that I built to do basic science. Then in the mid-1980s, I started building Mathematica, and then I started my second company, which I've now been running for 28 years. My second company, I made fewer mistakes. But as far as my personal productivity is concerned, I've tried to build a company which is a good amplifier for ideas that I have and a good way to turn ideas that I have into reality. The company is still reasonably small. It's about 700 people, mostly R&D people, and it's a private company. We've never had any investors, and that means that we're able to work on long-term kinds of things. We're not subject to worrying about whether the next quarter is going to look good for analysts and so on. We've been lucky enough to be profitable every year for the last 26 years, so that's helped in providing sort of a base for doing really long-term projects. So for me personally, I like to have at least one or two ideas every day that can turn into something real, and most days I manage to do that. What I've ended up doing personally, increasingly as the years go by, is to adopt a mode of trying to figure things out in public, in a sense. Because what I realized is, as a CEO of a company, you can just go off and figure stuff out. But if you do it in private, nobody knows why you made that decision, and nobody learns anything from the decision process that you went through. And so what I've increasingly ended up doing is figuring stuff out with groups of people. We happen to be a very geographically distributed company. I set a bad example 23 years ago by becoming a remote CEO, and so we've ended up with people scattered all over the world. And so my typical personal mode of life is I'm on the phone using screen sharing with people all day, every day, trying to figure stuff out and trying to solve strategy problems, technical problems, and so on. And that's been, for me, it's a very, very productive way to work. I've tried to sort of build this machine for taking ideas that I have and being able to to manage to get those ideas executed in an effective way. I mean, I think it also, for me, it's been really great to be exposed to so many different areas that we've been interested in working in, because every time, I've learned many different areas, and that's really helpful when you have to work in a new area, because there are always analogies and connections with previous areas. And I think even the things that I figured out about physics in recent years, I would never have figured out if I just stayed as a physicist for the last 30-something years. I figured them out because I've worked in a lot of different areas, and there are things that I can bring from those other areas to bear on problems that I was interested in, for example, in physics. So that's I'm always trying to figure out how to be more productive. And I have to say, I started doing this personal analytics stuff because I was curious to sort of measure my productivity, and sometimes it's kind of disappointing to see what you see from measuring your productivity, but overall it's been a positive thing to me to try to understand how I actually work and what things I'm actually good at doing and what things I'm not so good at doing. Well, okay, one or two more. Yeah, please.
Last question.
I mean, I'm happy to go on, but it's getting running. And
see your, hello? I can see your project collect a huge set of data, and there are many data sources around the world, internet, many channels. So can you share with us how you manage the data quality and how you can guarantee, for example, you raise the example of a population for New York. You know that data is consistently updated by different channels. So how you can tell which one is the most reliable and the one you should present back to us?
Yes. Okay, good question. So, we've tried to kind of accumulate in a consistent way as many different sources of data as possible. We've ended up discovering that nobody else is really trying to do this. And so we end up, like every year, we have a data summit conference in Washington, D.C., where we invite people who run the big data repositories from whom we're getting data and so on. It's been really interesting to get to know all these different sources of data. One of the things that's also true, even when we're getting public, let's say government or United Nations data, we end up getting to know the groups that produce this data, because that's the only way you get to understand what's really there, what's not there, how they get the data, what's going on. And with all of this data, there's always a story. There's always now, the other thing to say about data is when I started doing the Wolfram Alpha project, I thought one of the primary problems would be that we would find that for different kinds of data that we got, there will be 5 different sources, and we will be always discussing which one is the best source, which one isn't the best source, and so on. Here's the fundamental fact. The fundamental fact is, for most things that you want data on in the world, there are 0 sources. You simply can't get the data. Okay? So the next most common case is that there's one source. And then, when there's one source, that's the source you use. In much rarer cases, there are 2 or 3 sources of countries. There are a couple of different sources for that. And we go through all kinds of gyrations to figure out how to make things consistent. Because if you're not consistently using one source, you'll get inconsistencies. You get inconsistencies between money supplies and GDPs and this and that and the other. So that's one of the rare cases when you really had to worry about multiple sources of data. In most cases, there is typically one definitive source of data. There's one place that's collected, protein structures. There's one place that's collected meteorological records, these kinds of things. And so that's what we end up doing. Now, because we have a lot of different domains of data, we're able to do lots of cross-checking between different data domains. And for, I suspect, all of our data providers, we are the #1 source of bugs in their data, because we're always finding things that are inconsistent, and we then feed those back to the data providers. The other thing that's weird about data in the world is that you might think there are more sources of data than there actually are. Because if you take an area like, for example, financial data, there are all kinds of different companies that are selling financial data. The question is, financial, data about public companies and things. The question is, where did that data actually come from? And the answer is there's actually a very small number of sources. And it's really weird. You can kind of start drawing out the trade routes for this data, and people are, one company is getting the data from one place and they're reselling it to another company that's reselling it to another one. Sometimes there are even loops where a company is ultimately, one division is ultimately selling the data back to another division. It's really weird, and it's a very strange sort of kind of subterranean world of flows of data. We've spent a decade or so trying to unravel, how this all works. But the main bottom line is there are very few domains in which there is more than one primary source of data. Now, another thing that happens, which is very frustrating to us, is there are sources of data where it's the one source and we know the answer is wrong. So, for example, if you look at some socioeconomic data, for instance, there's all kinds of funky stuff where countries are, for one reason or another, misreporting certain kinds of data, we can quote what's reported, but there's no way we can know more than that. I mean, I'll tell you one funny story perhaps about data quality. So if you if you ask, let's see if we can actually do it. This probably won't work, but if you make just a kind of silly query, the number of turkeys in Turkey, okay? I don't understand this. How does this? What happens here? This is what? Tell me what. Okay, so here's the question, you guys. Why is this happening? How can I stop it happening? Okay, so there you go. For just a moment here, we'll see the time history of the number of turkeys in Turkey. Okay. So you see there's that weird peak. Okay. So the question is, what the heck is that peak? Right. So we talked to the people in the Food and Agriculture Organization, UN, organization that generates this data. They said we have no idea what that peak is. Go ask the Turkish Statistical Organization. So we go ask them, and eventually, after many steps, we're talking to the actual person who's responsible for this data, who says, well, we take the census of livestock every year, and there's this book that's a physical book that has all the data from the census, and says, I'll go and look at that book. Comes back and says, oops, the book for that year is missing. So, that's sort of the end of the line. Then we're stuck. And we can, what we try to do whenever we can is to footnote the data that we're giving to be able to tell people, so there's some cases where we know things can't be accurate. Like, for example, if we're giving tide data, the tides will depend not only on historical computed tides, but also on whether there happened to be a storm near Dubai the day before. So we have a footnote that says that. Now, one of the challenges that I don't think we've yet really figured out how to solve is when people are using data through our language, they're often building a big stack of stuff on top of a particular piece of data. And when they're using it in Wolfram Alpha, they can see the footnote. By the time they're using it in a big stack of data in the language, the end user is never going to see that footnote. So it's an issue. That's a place where it's important that we make the data as consistent as we can, and we've made a great effort to do that. But there's a limit to what we can do because we can't go out and do a census of the number of turkeys in Turkey in 1999. That ship has sailed. So. Okay, well, I could go on for ages here, but I think probably. All right, a few more questions.
Pardon me for a couple more questions. The first question is, can you comment on the advancement or the changes of the semiconductor business, how that has anything to do with the way you conduct your computation? The second question is that, do you think it's necessary for the algorithm or the architecture of the CPUs to change in order to be more consistent and synergetic to the right way of computation? Because in the end, you know that the physics world does not necessarily evolve the same way as the computational world evolves. So, sort of related is that do you envision Wolfram or you get into the hardware business, come up with the ARM for Apple or some particular type of CPU for Wolfram?
Okay, those are interesting questions. So in terms of the general evolution of the semiconductor industry and its effect on us, there are these different thresholds that one passes. When computers get fast enough, a new thing becomes possible. So for us, there's sort of how big a layer of software can be running while still having good human reaction time, so to speak. And so, you know, what's been important to us is that we've always sort of said we're going to build software the way we think it should be built, and eventually the computers will be fast enough to be able to run things the way we want them to be run. And so, you know, every few years there's been some new threshold passed. So, for example, being able to have sort of good interactive performance using our language is something that threshold does, you know, arithmetic better, does this kind of thing better, that kind of thing better. We've at the beginning we always used to chase every one of those. We used to say, great, we're going to support this, we're going to be able to optimize these operations. Mostly different kinds of things. So, in terms of our interest in hardware and so on, it's I don't know. Hardware always scares me. Software, at least, you know, there's a certain simplicity to software. But that being said, we've been quite involved in these embedded processor things, and one of the things we'd like to see happen is for our language to be used essentially as a shell or a kind of operating system for sort of intelligent embedded devices, and something where we can actually expect that, you know, when you're developing some kind of thing, you know, toaster, whatever else, you can just assume that you're going to be able to do sophisticated image processing and things like that right in the embedded processor. And that's something that we're really interested in having happen. I also have some interest in the ways that sensors are set up. One of the things that we've done, we have a little project that we did, which may or may not work here, that